and do one numerical on the concept. This is not in NCERT. But it's an important feature, you should know this thing. See, while calculating the expression of acceleration due to gravity, which is gm by r square, we have considered that Earth is at rest. But actually, Earth is not at rest, it's rotating about its axis. So, due to rotation of Earth, there is one force which is acting on the body, and that force is so this is Earth. This is the axis passing through it. Now, if I don't consider the rotation of Earth, this is center of Earth, and I place a body of mass m here. So if I am not considering the rotation of Earth, then the only force acting on the body is gravitational force, Fg, towards the center of Earth. So this is the gravitational force which is acting on the body towards the center of Earth. This is gravitational force. But once this Earth starts rotating, due to rotation of Earth, a centrifugal force will act on the body in a direction away from the center. A centrifugal force will act on the body away from the center of the Earth. So due to centrifugal force, the net gravitational force will decrease. The net acceleration due to gravity will decrease. So due to rotation of Earth, a centrifugal force will act on the body away from center. So away from the center and along the body, a centrifugal force will act, which decrease the gravitational force and hence acceleration due to gravity. It's a very common force. You must have experienced this force if you sit in a ride which is rotating. And in that rotating ride, you experience a force in outwards direction. That force is centrifugal force. Or if you are sitting in a car and that car takes a circular turn, then a force will try to pull you out of the center of the circular turn. That force is centrifugal force. So you knew latitude, right? You know what is latitude? So if I say this is equator, equator means a horizontal plane passing through the center of Earth. This is the mass, and with respect to this equatorial plane, this line is making an angle lambda. This angle lambda is basically latitude. This is mass m, this is equatorial plane. This line is making an angle lambda, the line joining the point on the surface of Earth to the center of Earth is making an angle lambda with the equatorial plane. This lambda is known as latitude. Lambda is known as latitude. So the expression for acceleration due to gravity is g prime is g minus r omega square cos square. So this g is the same value, it's 9.8 meter per second square. This omega is angular velocity of rotation. This is angular velocity of rotation. You can write your omega as it's 2 pi over capital T. This is omega, 2 pi by T. And here this lambda is the latitude. This lambda is the latitude. You must have done latitude in your geography class up to class 10. There's two angles, one is longitude, another one is latitude. And this
Yes, sir.
time period of rotation. T is time period of rotation. Time period of rotation of Earth. In general, this time period is 24 hours. Now, we can check the effect of rotation of Earth at two extreme points, one at the equator and then another at the pole. So if I want to check the value of this variation in acceleration due to gravity at the equator. At equator, okay, can you guess the value of lambda at equator? The latitude, what's the latitude of equator? For equator, latitude is 0 degrees. So instead of this lambda, you can substitute 0. So yours G prime will be, it's G minus R omega square cos square 0. Cos 0 is 1. So G prime is G minus R omega square. This is at equator. If you want to check the same thing at poles lambda is 90 degrees. So G prime is G minus R omega square cos square 90, cos 90 is 0, so G prime is 0. So you can check there is no effect of rotation of Earth at poles, but there is an effect of rotation of Earth on equator. As ever, capital R is radius of Earth. So due to rotation of Earth also, the value of acceleration due to gravity decreases. But it doesn't affect at poles. At poles, there is no effect of rotation of Earth on the value of acceleration due to gravity. So that is the effect of rotation of Earth on the value of acceleration due to gravity. Let's do one question. Calculate angular velocity of rotation of Earth so that value of acceleration due to gravity is 0 at equator. Try to solve it. You know the value of acceleration due to gravity at the equator. Calculate the value of omega so that it reduces to 0. Okay. See, this is very straightforward. You need G prime, which is G minus R omega square. This is the value of equator, which is equal to 0. Yes, Noor is correct. Fazil, just take care of units. Huh? So G is R omega square. You can write your omega square as G by R. Then you can write your omega as root over G by R. This is omega, which is root over G by R.
Sir?
Yes. Yes, Fazil.
Do we have to like substitute the values or like simply?
You're asked, Fazil, you're not audible. Can you repeat your questions?
Sir, can you hear?
Yeah, now you're audible.
Sir, do we have to like substitute the values or no need?
Yes, it's better if you substitute the values. That's 9.8. And the value of R is 6.4 into 10 raised to the power 6 radian per second.
Okay.
And if you want to calculate time period, then you can write your omega as 2 pi over t, which is root over g by r. You can simply cross multiply them, then your time period will be 2 pi, it's root over r by g. But while substituting the numerical value, just take care of units. Both numerator and denominator should be in single unit. They should be in SI unit. Sania, is it clear?
Yes, sir.
Okay, let's move on to next question. So that was all about acceleration due to gravity. You will get at least 1 or 2 questions from acceleration due to gravity. It's a major topic. After acceleration due to gravity, the next thing is its gravitational field. The next one is gravitational field. So I'm erasing it. So see, gravitational field. What is gravitational field? Gravitational field is simply the space around the mass. It is the space around the mass in which its gravitational force can be experienced by any other mass. It is the property of at least one mass. So to calculate gravitational field, you need at least one mass. So if I take a capital mass m here, the radius of this capital R is this. So there is a region around this capital M in which region the gravitational effect of capital M exists. And that region is known as gravitational field of capital M. So if I take any mass, like if I take Earth, then there is a region around the Earth within which the gravitational field or the gravitational effect of the Earth exists. And that region is known as gravitational field. But that gravitational field is not visible. Just by looking at the mass, you can't decide that up to what region its gravitational field exists. So to check whether field exists or not, this is the mass which is generating field. So we call this as source mass. I have to check whether the field exists or not. Now, since gravitational field is not visible, so we take an indirect method. We take another mass, small m. We call this mass as test mass. If this test mass experiences gravitational force, then I would say that over this point, gravitational field of capital M exists. But if this small m does not experience any force, that simply means the field does not exist. It's a very simple thing. If due to this capital M, this small m can experience a force, that means the field of capital M exists here. But if it does not experience a force, that means field does not exist. In the language of field, the force on small m is due to gravitational field of capital. It's due to gravitational field of capital. So when we talk about field, the mass first generate a field around itself, and in that field, another mass will experience a force. This is how we do it. Okay, so the next thing is So this is the gravitational field. Now, how would you calculate the field? When we calculate the strength of field, the quantity is known as gravitational field strength or intensity. Gravitational field strength or intensity. So let's check what is gravitational field strength or intensity of. Over this point, we represent gravitational field intensity by I. See, let's say you have a mass capital M. This is a source mass. This is source. Over this point, there is one mass small m. The separation between capital M and small m is something. I have to calculate field over this point, the field of capital. So to calculate field of capital M at this point, I placed a test mass. This is test mass. If this test mass is placed in the field of capital M, then this test mass will definitely experience some force. So here F is force on small m due to field of capital. So the gravitational field intensity that we represent by I is the ratio of force experienced by small m divided by the magnitude of small m. This is the definition of gravitational field intensity. So gravitational field intensity at a point due to source mass is the ratio of force experienced by test mass divided by the magnitude of test mass. It's a vector. Its direction is towards capital M. So I is field. I should write gravitational field. Whenever I write field, that means gravitational field of capital. The next point I'm writing here, direction of field, gravitational field is towards capital. The direction of field is towards capital. Its SI unit is, its force by mass, its SI unit is Newton kg units. So this is about gravitational field. So this is the general expression of gravitational field. Now the formula of gravitational field is different for different types of masses. Like for a point mass, the formula is different. For a rod, relation is different. For a disk, relation is different. So the relation is different for different types of masses. So let's start with gravitational field of a point mass or a sphere. In your syllabus, you just have to solve a sphere or a point mass. No need to calculate disk or rod. It's not a part of your syllabus. In your syllabus, only you need gravitational field of a point mass or for a sphere. For both point mass as well as sphere, the relation is same. So you have a point mass, capital M, and you want to calculate the field at a distance r. So at a distance r, the expression of field is, it's gm by r square. This is the expression of field for a point mass. It's gm by r square. And the direction of field is always towards the mass. Direction of field is towards the mass. direction of field is towards capital M. So if you have a mass capital M, then field due to this capital M is towards capital M, which is I is gm by r square. And unit is same. So we can do a simple problem on the same concept. Let's say you have a mass of 2 kg and I ask you to calculate field at a distance of 10 meter from the point mass. Then at a distance of 10 meter from the point mass, the expression of field is this, it's gm over r square. If I substitute the values, your g is 6.67 into 10 raised to the power minus 11. Capital M, which is 2 kg, r square, which is 10 square. So I is 4, 3, 3. 13.34 into 10 raised to the power minus 13. It's Newton per kg. Is it clear? Simple relation.
Yes, sir.
Yes, sir.
But this question would be very simple. You won't get problems on a single mass. You can get problems where you have multiple masses, 2 or 3 masses to calculate gravitational field. That problem is known as gravitation. If you have more than 2 masses, then we will use superposition principle. So superposition principle says if you have a number of masses m1, you have another mass m2, you have a mass mn. Due to these n masses, you are calculating field over this point. To calculate field over this point P due to n masses m1, m2, mn. Due to m1, this is the direction of field I1. See, for calculating field, you don't need second mass. Field is a property of a single mass only. If you have this relation, you don't need another mass. Only due to 2 kg, you can calculate field. You have n masses here, you're supposed to calculate field over this point. To calculate field at this point, we will first calculate field due to individual masses. If I call this separation as R1, I call this separation as R2, I call this separation at R3, Rn. Then I can write I1 as it's gm1 by R1 square. Similarly, your I2 is gm2 over R2 square. Similarly, your In is it's gmn over Rn square. For net field at P, you can simply add them up vectorically. So the net field at P is just vector sum of I1, I2 and I. This principle is same as that of superposition principle of force. We did superposition principle for force too. So it says for system of n interacting point masses. Okay, I don't have. For system of n interacting point masses, net field at a point is vector sum of field due to individual masses. Okay, let's do a simple problem on this concept. You have 2 masses, a mass of 10 kg and a mass of 5 kg. They're separated by some 10 meter. You're supposed to calculate the position of a point at which the net gravitational field is zero. That means you're supposed to calculate the position of a point where field due to both the masses cancel each other. So calculate position of point at which gravitational field due to both the masses cancels each other. Sometimes this point is known as neutral point. This is also known as neutral point, point at which net gravitational field is zero. So the calculations are straightforward. This is mass 1, this is mass 2. Sania, can you guess the direction of field over point n due to 10 kg? This is my right, this is left. What's the direction of field? It's towards right or towards left? For direction of
right.
For direction of field, always remember, direction of field is towards the mass. Towards
left.
The direction of field is always towards the source mass. So if you are calculating field over n due to the mass 1, then this is the direction of field itself.
Yeah.
Similarly, due to this 2 kg mass, the direction of field is towards 2 kg mass. Yeah. Right?
Yes.
So the net field is vector sum of I1 and I2. That should be equal to 0. Let's say the separation of this neutral point from 10 kg mass is x. So Fazal, what is this separation? How much is this one?
10 minus x.
It's 10 minus x. So the net vector sum of field is 0. So if you can check, I1 and I2 are acting in opposite directions. Now if they are acting in opposite directions, you can directly subtract them. I1 minus I2 is 0. Or you can simply write I1 is equal to I2. I2 you can write, this is gm1 by x square, which is equal to gm2 over 10 minus x square. This g will cancel this g. You can substitute the value of m1. m1 is 10 kg, m2 is 5 kg. So it's 10 over x square is 5 over, it's 10 minus x square. To solve this equation, you can take roots on both the sides. So it will be root 10 by x. I'm taking square roots. Square root on both sides. Root 10 over x, and this is root 5 over 10 minus x. So if I cross multiply them, this is root 10, 10 minus x, which is root 5 multiplied by x. So you can write this as it's 10 root 10 minus x root 10 is x root 5. I can take this thing to the right hand side. It's x root 10 plus x root 5. So this is 10 root 10 is x. It's root 10 plus root 5. So your x comes out to be, it's 10 root 10 divided by root 10 plus root 5. This is the value of this. It's 10 root 10 by root 10 plus root 5. Is it clear?
Yes, sir.
Yes, sir.
So this is how we calculate neutral points. So instead of this point masses, he can give you spheres, he can give Earth and Moon and can ask to calculate a neutral point. The method would be same. Only the masses will change. Masses and separation would change. Okay, so there is no field at point N. So if I place let's add one more part in the same question. Calculate force on mass of 100 kg placed at neutral point. Can you guess the force on a mass placed at the neutral point? You can think in this way. If I take this pen and if I release it, it's going downwards. Sania, why is it going downwards? If I take this pen and I release it, this pen is going downwards. Why is it going downwards?
Because gravitation.
Good, gravitational force. We can explain the same thing. Instead of gravitational force, we can use gravitational field. I can rather say that there's over this point, the gravitational field of Earth exists, and that gravitational field of Earth exerts force over this point. At this point, gravitational field of Earth exists, and that gravitational field of Earth exerts force over the pen. So if at any point force is exerted by field. I'm repeating again. Gravitational force is exerted by gravitational field. If at some point gravitational field is zero, that will mean that gravitational force is zero. So now can you guess the force acting at a point mass of 100 kg at neutral point? At neutral point, gravitational field is zero. Yes, gravitational field is zero. If gravitational field is zero, then you can write that your gravitational force, you can even write your force as mass into field. Since gravitational field is force by mass, you can write your force is mass into I. So if your I is zero, so your force comes out to be zero. So at neutral point, there is no field, that means no mass, no force. So if at some point gravitational field is zero, that will simply means that gravitational force is also zero. The next topic is, we have done gravitational field. The next is gravitational potential energy. The next is gravitational potential energy. So if you have two masses, a mass m1, another mass m2, they are placed at a separation arc. Okay, just tell me, will these masses attract each other? They are placed in free space, m1 and m2.
Yes.
Yes, they will attract each other. Due to which force? Due to which force they will attract each other? Which force?
Gravitational field.
Gravitational force. And gravity is conservative. This we did in chapter number 6, like in work, energy, and power. This we did in work, energy, and power, that gravitational force is attractive, gravitational force is conservative. Whenever we have a conservative force, corresponding to that conservative force, we have potential energy. So due to gravitational force, system will have gravitational potential energy. Gravitational potential energy. So to derive that potential energy, we use we take the help of work done. What we really do, we take a mass m1 here, we put another mass at infinity. Infinity means a point where gravitational field of small m1 vanish. At infinity, the gravitational field of m1 vanish. Gravitational field vanish, that means there is no interaction between m1 and m2. There is no potential energy. Then we will calculate work done in carrying this m2 from infinity to a point at a finite separation from m1. So the work that we do to bring this m2 from infinity to this point gets stored in the system in the form of potential energy. So work done in carrying m2 from infinity to finite separation gets stored in the system in form of potential energy. In form of potential energy. So this is how we derive potential energy. I'm not deriving the thing. I'm just writing the exact final result. That work done comes out to be, if I call this point as A, then work done in carrying m2 from infinity to A. If I derive this result, then this work done comes out to be it's minus of G m1 m2 by R. And this work done is exactly equal to potential energy. This work done gets stored in system in form of potential energy. So you can write that your potential energy is equal to work done, which is minus of G m1 m2 by R. We will derive this result tomorrow. Like how to calculate this work done, we'll derive it tomorrow. It's a 10 to 15 minutes derivation. But you should remember this result that the potential energy of a system of 2-point masses is minus G m1 m2 by R, which is equal to work done. Sometimes this work done is also known as work done to make the system. See, when m1 and m2 were at infinite separation apart, then there was no interaction between them. There was no work done. There was no interaction, there was no system. But when you bring this m2 from infinity to A, then they start interacting with each other. They start exerting force over each other. When they exert force over each other, then we say it's a system. In physics, interaction means bodies exert force over each other. So I'm repeating it again. When m1 and m2 are at infinite separation, there is no interaction between them. They are not exerting any force over each other, so it's not a system. But when I bring this m2 from infinity to A, now m1 and m2 are at a finite separation apart. So now they will interact each other. So now this we can call this as a system. So this W work done, you can write this W as work done to make the system. This is potential energy. Now there are few discussions over this expression. U is minus of G m1 m2 over R. You can get objective questions on this result. The first is the significance of this negative sign. What does this negative sign signifies? This negative sign simply shows that the force between m1 and m2 is attractive. Whenever you have attractive forces in your system, the potential energy is negative. So this negative sign shows that force between M1 and M2 is attractive. This is the significance of this negative. Then he can ask you to calculate the maximum value of potential energy. So if I take R equal to infinity, can you guess how much is U if your R is infinity?
Minus Jm1 M2.
1 by infinity is 0, so it comes out to be 0.
Yes.
This is the maximum value of potential energy, 0. Because all other values would be negative. If on a number line I write minus 10, minus 9 and 0, which one is the maximum number? I'm even taking 1000.
0.
So that's why. If you don't take R equal to infinite, then the value of all values of U would be negative. But if you take R equal to infinite, then your U will be 0, and that is the maximum value of potential. Okay, after this value of this potential energy, the next is, let's do few, there's one more small concept, which is potential energy difference. In potential energy difference, what we do, let's say this is mass M1. I first place mass M2 at a separation here I place mass M2 at some point A, and I call this point as the initial point. This separation is R. Then I take this M2 to a point B, and I say that this separation is R. Now, since both R1 and this is the final position. Now, since R1 and R2 both are finite separations, that means at position A, system will have some potential energy. At position B, system will have some potential energy. So, potential energy of system when M2 is at A. Fazil, what is the expression of potential energy when M2 is at A? Both are point masses.
Minus G M1 M2 by R.
Very good. Minus M1 M2 by R. Similarly, you can write UB. Yes, Noor, how much is UB?
So minus G M1 M2 by R2.
You're supposed to calculate potential energy difference. Potential energy difference. This we can write delta U, which is always final potential energy minus initial. This is final and this is initial. So you can write this as UB is minus of G M1 M2 by R2 minus of UA, which is minus G M1 M2 by R1. So the change in potential energy is it's minus of G M1 M2 by R2 plus G M1 M2 by R1. So the change in potential energy is it's G M1 M2. You can take this as common. This is 1 by R1 minus 1 by R. So this is the expression of potential energy G M1 M2 1 by R1 minus 1 by R2. Always remember that this R1 is your initial separation and R2 is your final separation. So very common question on this potential energy difference is calculate potential energy difference between 2 points, one on the surface of Earth, another at height h. So this is Earth. The mass of Earth is capital M. The radius of Earth is capital R. I take one point on the surface of Earth, that's small m. I take another point at a height h. Another point at a height h. This is point 1, this is point 2. So your R1 is your R, your R2 is R plus h. So one is on the surface of Earth, another is at height h, so that's R plus h. So if I calculate potential energy difference, the expression was G M1 M2 1 by R1 minus M by R. This was the expression.
Yes.
Just substitute the value. So it's G M1 M2. R1 is R minus 1 by R plus H. So this is G M1 M2. You can do one thing. You can take this R into R plus H as LCM. This will be R plus H. Or instead of M1 and M2, I'm using small m and capital M. So I'm taking small m1 as capital M and m2 is small. It's capital M multiplied by small m. It's capital M multiplied by small m. Capital M into small m. R plus H minus R. This R will cancel this R. The change in potential energy comes out to be its GMM into H by R into R plus H. Is it clear up to this point?
Yes, sir.
Yes, sir.
Next, we can take R common from this term. If I take R common, then this will be GMMH over R. From this R plus H, I'm taking as one R as common. So inside, I'm left with 1 plus H by R. Sania, is it clear? Taking R common means dividing both the terms by capital R.
Yes, sir.
Divide this by capital R, it's 1 H by R. So this change in potential energy comes out to be its Gm by R square 1 plus H by R into MH. Okay, Sania, what is this Gm by R square? So this delta U comes out to be GMH by 1 plus H by R. This is the change in potential energy. Now, if I say that H is very, very less than R, height is very, very less than the radius of Earth, then H by R is almost zero. If it's almost zero, then potential energy comes out to be mgh. So the potential energy at a height h is mgh. Change in potential energy is mgh only if height is very, very less than the radius of Earth. Otherwise, the exact expression is this. This is mgh by 1 plus h by r. So mgh comes when height is very less than the radius of the Earth. This could be your objective question, that when change in potential energy is equal to mgh. This is equal to mgh only if your height is very less than the radius of the Earth. Okay, solve this question. This is very straightforward. You have a mass of 10 kg, another mass of 5 kg, placed at a separation of 10 meters. Calculate potential energy of the system. Second, I need work done to make the system. Third, work done to break the system. First part is trivial, huh? The potential energy is minus of G m1 m2 over R. Keep on substituting the values. G is 6.67 into 10 raised to the power minus 11. M1 is 10, M2 is 5, R is 10. So this 10 will cancel this 10. So it's minus of 5, 3, 3, 3 into 10 raised to the power minus 11. So that's the answer of part 1. The second part, work done to make the system. We did this in definition, that work done to make the system is equal to potential energy, which is minus of 33.35 into 10 raised power minus 11. Okay, now what should be the work done to break the system? Can you guess how to calculate work done to break the system? If work done to make the system is this?
33.35 into 10 raised to minus 1.
Work done to break the system is negative of work done to make the system. So it's negative of minus 33.35 into 10 raised to the power minus 11. So it comes out to be 33.35 into 10 raised to the power minus 11 joule. This is the work that we will do to break the system. That's the work done to break the system. 33.35 into 10 raised to power minus 11. So that was potential energy for a system having 2 masses. But instead of 2 masses, if you have 3 of system having 3 or 4 masses, let's calculate potential energy for a system having 4 masses. Let's say we have a system having 4 masses, M1, M2, M3, M4. This is A, this is A, this is A, this is A. This is the diagonal. This is another diagonal. It's A root 2. This is A root. So to calculate potential energy of this type of system, you can divide this system in system of each 2 masses each. Like we can first calculate potential energy of M1 and M2. Then we can calculate potential energy of M1 and M3. Then we can calculate potential energy of M1 and M4. Then M2, M3, M2, M4. We have to decide the total number of interactions. Then we will calculate potential energy corresponding to each interaction. The first interaction is between M1 and M2. The separation between M1 and M2 is A. So it's minus of G M1 M2 by A. Next, second interaction of M1. The second interaction of M1 is with M3. The separation between them is A root 2. So that's minus G M1 M3 over A root 2. Then this M1 will interact with this M4. This is minus G M1 M4 over A. So these are all interactions of M1. Then we take interactions of M2. M2 can interact with M1, but we have already counted this interaction. If you say M1 interact with M2, or you would say M2 interact with M1, they're the same interaction. We will not take this interaction twice. It's one interaction. Then we can take interaction of M2 with respect to M3. So this is minus G M2 M3 over. Next is M2 with M4. We have not yet considered this interaction, M2 with M4. Minus G M2 M4 by AB. The next comes the interaction of M3. Interaction of M3 with M1. We have already counted it or not? Interaction of M3.
Yes, sir.
We have already counted. When I say that M1 interact with M3 this one, we have already counted this interaction. We will not consider it. What about M3 and M2? Interaction of M3 and M2?
Yes.
Done. We have already considered this interaction here. The interaction that left is M3 and M4. So that's minus of G M3 M4 divided by. So you have in total 6 interactions. So this is the potential energy of the system having 4 masses. So if you have 3 masses, then correspondingly you have to count the number of interactions. So that was about potential energy. After potential energy, the next topic is potential. Gravitational potential. See, gravitational potential, just like gravitational field, it gives you information about the gravitational properties of a mass. Just like field, it gives you information about the gravitational properties of a mass, around a mass. But instead of vector, this potential is a scalar quantity. So I'm not writing the exact definition. I'm writing a statement which will help you to understand what is exactly gravitational potential. It defines gravitational property around a mass in scalar form. It's almost doing the same thing as that of gravitational field, but gravitational field is a proper vector quantity. But this potential is not a vector, it's a scalar quantity. Definition. The exact definition of potential. So it can be defined as work done in carrying a unit mass from infinity to a particular point against the field. See, let's say you have a mass capital M. This is my source mass. I ask you to calculate the potential of this source mass over this point P. This is a source mass. This is generating some potential over T. So to calculate that potential, I choose infinity. I take up test mass M here. Then I calculated work done in carrying this test mass from infinity to this P, that I call W infinity P. It's work done in carrying test mass in carrying test mass from infinity to P. So potential at P is, we represent potential at Vp. This is work done in carrying test mass from infinity to P divided by the magnitude of test mass. There's a very small difference between potential and potential energy. In potential energy, the whole of this work done was equal to potential energy. But for potential, divide this work done by the test mass. So this is the definition of potential. It's a scalar quantity. Its SI unit is joule per kg. I'm repeating again. We are first calculating work done in carrying test mass from infinity to a point. Then we divide that work done by the magnitude of test mass. This ratio is known as potential. Its SI unit is joule per kg. This is general definition of potential. So this was general definition of potential. This definition is valid for all types of masses. You can have a point mass, you can have a sphere, you can have a rod, or you can have a sheet. Whatever be the mass, the type of mass configuration you have, this expression is valid. But it's not very helpful for numericals. For numericals, you need an easier expression. So we can derive an expression for potential. The proper name is gravitational potential. For a point mass or a sphere. In the last section, what we did was the general definition, which is valid for all types of mass configuration. When I say types of mass configuration, means your massive body could be a point mass, your massive body could be a sphere, your massive body could be a rod, or your massive body could be a sheet, could be anything. But if you have a point mass or a sphere, so you have a mass m, and you're supposed to calculate potential at a separation r. So at a separation r, the expression of potential is minus of gm by r. In field, it was gm by r square, but here it's minus of gm by r. This is gravitational potential for a point mass or for a sphere. It's minus of gm by r. This negative sign again shows that force is attractive. It shows attractive, force is attractive. Solve this simple question. This is a mass of 10 kg. At a separation of 10 meters from this mass, calculate gravitational potential. Let's call this as P. Calculate gravitational potential at P. So minus 6.67 into 10 raised power minus 11. Your mass is 10 kg divided by r is 10 meter, gets cancelled out. So potential is simply minus 6.67 into 10 raised power minus 11 joule per kg. So this is for a system having just one mass. But if you have a system having, say, two or more masses, then just like field, calculate potential due to individual mass and then add them up. So gravitational potential due to system of n point masses. So it's just like field, but the difference is instead of adding them vectorically, it's a scalar quantity. You will add them up algebraically. This is mass m1, m2, mn, and this is point. From m1, this separation is r1. mn, this is r. So first calculate potential due to each of the individual mass. So for first mass V1, this is minus of G M1 by R1. Mass M2, it's minus of G M2 by R2. For Mn, it's minus of G Mn by R. This is the potential. Solve this question. You have two masses, a mass of 10 kg and a mass of 5 kg. They are placed at a separation of, let's say, 10 meter. I need potential over this point. From 10 kg, this separation is 2 meter. You can calculate this separation. Calculate potential at T. So if I calculate potential, let's call this as mass 1, this as mass 2. This separation would be 8 meter, right? The distance between both the masses is 10 meter. So net potential would be the sum of potential due to individual masses. Due to first mass, potential is minus G. Its mass is 10 kg. R is 2 meter. Plus its minus G. Mass is 5 kg. Separation is 8 meter. So you can take minus G as common, or I can solve it. 10 5s are. If I cancel this thing, it's 5 by 8. So it would be 0.622. So this comes out to be minus 5G 62. Minus 5G minus 0.622G. So it's minus 5.622G. You can even substitute the value of G, 5.622, into 6.67 into 10 raised to the power minus 11. So this is around some 30. 5, 6, 30. I'm using calculator. So this is 5.622 into 6.67. It's 37.49. Ten raised power minus 11. It's joule per kg. Always remember this thing. Joule per kg. So that was about gravitational potential. So the next thing is you can relate gravitational potential and potential energy. It could be a 1 marker question in objective. Relation between potential energy and potential. See, potential energy was equal to work done. This is potential energy. But potential is work done divided by mass. This is potential. So you can easily relate them. Like instead of, this is the definition of potential energy that we did. This is definition of potential. You can easily substitute 1 in 2. When you substitute 1 in 2, then V comes out to be U by. Or you can write that your potential energy is mass into potential. So that's the relation between potential energy and potential. That potential energy is mass into potential. Second last topic, that's escape velocity. So escape velocity is the minimum velocity with which a body must be projected from the surface of a planet so that it escape its gravitational pull. So I'm not writing the formal definition. The minimum velocity with which a body must be projected from the surface of planet or moon or any star so that it escape its gravitational pull and comes at rest at infinity. See, if I project this pen upwards, then this pen will go up to a certain height and will come back to my hand. The reason is, up to this height, this is within the gravitational field of Earth. That's why it's coming back to Earth. It's coming back to my hand. But if I project this pen with such a high speed that it goes to infinity, at infinity there is no gravitational pull of Earth, so it will never return. It will stay at rest at infinity. So escape velocity is the velocity with which if we project a body, then it will escape the gravitational pull of Earth and comes at rest at infinity. So this is, let's say this is Earth. Mass is capital M, this is Earth. This is a body of mass M. You are projecting this body with a velocity which is escape velocity. So it will reach up to infinity, and at infinity it will come at rest. So since it at infinity, the kinetic energy of body is zero. Since body comes at rest, so its kinetic energy is zero. There is no interaction at infinity between body and Earth. So potential energy of body. Can you guess the potential energy?
0.
Yes.
0.
So you can say that total energy of body at infinity is sum of kinetic energy plus sum of potential energy. Both are zero, so this is zero. To calculate the expression of potential energy, you can even use conservation of energy. So I'm using conservation of energy at a point on the surface of Earth and at another point of at infinity. So if I'm using conservation of energy, on surface of Earth and at height h, at not height h, at infinity. So conservation of energy means kinetic energy at surface of Earth plus potential energy at surface of Earth is equal to kinetic energy at infinity plus potential energy at infinity. Since there is no force like friction, so energy should remain conserved. So how much is the kinetic energy at the surface of Earth? If I am projecting this with this escape velocity VE, half into V square. So I'm applying all energies for this body of mass and which we are projecting. Potential energy, if the radius of Earth is R, then its potential energy is minus G. Mass of M, mass of body divided by R. And this is 0. So you can write this as, this is half M VE square is GMM by R. See, you can cancel this M. M will cancel this M here. Your escape velocity is, it's 2 gm by r with a v. So this is the escape velocity. So if you look at this relation carefully, that you will notice that this escape velocity depends only on the mass of the planet. It's depending on, if you are projecting from Earth, then this is mass of Earth. It depends on mass of planet from which you are projecting. This is capital R, it's radius of body. It depends upon the radius of body, radius of planet from which you are projecting. So escape velocity is absolutely independent of the mass, shape and size of the body. It depends on the planet from which you are projecting. So if you are projecting from Earth, then the escape velocity will depend on Earth, parameters of Earth, not on the parameter of body. Next, we can also convert this expression of escape velocity in terms of acceleration due to gravity. So the escape velocity is root over, it's 2gm over. If you want, you can convert this in terms of acceleration due to gravity. To convert this in terms of acceleration due to gravity, what you can do, you can multiply this numerator and denominator by r. So it comes out to be root over 2gm by r square into r. What is gm by r square?
G.
This is about g. So the relation of escape velocity comes out to be root 2g. If you want to calculate this value for Earth, just put g equal to 9.8 meter per second square and put r equal to 6400 kilometer. That's 6.4 into 10 raised power 6 meter. If you substitute all these values, then the expression of escape velocity comes out to be 2 into 9.8 into 6.4 into 10 raised power 6. When you solve these numbers, it comes out to be 11.2 into 10 raised power 3 meter per second. You can convert this in kilometer. You can write this as kilometer. So that's 11.2 kilometer per second. So this is escape velocity for Earth. So if you want to project a body from Earth to infinity, then the velocity that you will provide will be 11.2 kilometer per second. This is escape velocity for Earth. Always remember that escape velocity is independent of mass and size of body. It depends on mass and size of planet. Planet or moon from which you are projecting it. For objectives, you can be asked to write this expression in terms of density and volume. So in terms of density, see, escape velocity is root over 2gm by r. The density of Earth is mass divided by volume. So mass is m, since Earth is a sphere, so its volume is 4 by 3 pi r cube. So you can write your m as it's 4 by 3 pi r cube rho. You can substitute the values here. So escape velocity comes out to be, it's root over 2g 4 by 3 pi r cube rho over r. So this r can cancel this cube. It comes out to be root over 248 8 by 3 pi g rho r square. This r will cancel this cube, so you're left with r square. So maybe in a numerical or in objective, you can be asked to express this escape velocity in terms of density and volume. So if I throw a body with velocity equal to escape velocity, then body will come at rest at infinity. That's why kinetic energy at infinity is 0. But if I throw a body with a velocity greater than escape velocity, then it will not stop at infinity, continue to move with a velocity at infinity. So the question says a body is projected with velocity v greater than escape velocity. So I projected this body with a velocity v which is greater than escape velocity. So calculate velocity with which it moves at infinity. So you projected a body with a velocity which is quite greater than escape velocity. So you're supposed to calculate the velocity with which the body will move at infinity. So for this thing, what you can do is this is Earth. You projected this body of mass m with a velocity v in upwards direction. And remember, this v is greater than escape velocity. At infinity, this body will continue to move with some velocity. You have to calculate this velocity. This v prime is velocity of body at infinity. This calculation is very straightforward. If I give this example, like I give body an energy of 10 joules, and I say that out of this 10 joules, 6 joule is spent in sending this body from the surface of Earth to infinity. 6 joule body spent in moving from surface of Earth to infinity. Total I provided 10 joule. So how much is left with the body at infinity? How much energy is left with the body?
4 joules.
4 joule. So this is the 4 joule energy with which the body can travel at infinity. So I can simply write this as kinetic energy provided to body. You have projected the body with velocity v, so the kinetic energy that you provided the body is half mv square. So energy that body spent in moving from surface of Earth to infinity. So the energy that body spent is simply half the kinetic energy corresponding to escape velocity half mv square. The kinetic energy with which body travel at infinity. So the kinetic energy with which this body travels at infinity is half m v prime square. So you can simply write this as this is the total energy that you provided to the body. This much of energy is used in escaping from the field of Earth, and this is the energy which is left. So this is the total energy half mv square. I used this energy half mve square to escape outside the gravitational pull of Earth, and this is half mv prime square. So half m gets cancelled out. So I'm left with only v square minus ve square is v prime square. So the v prime comes out to be its root over v square minus v square. V is escape velocity. This is escape velocity. So this is the velocity with which the body moves at infinity, with which the body travels at infinity. We provide this total energy. Out of this total energy, this much of energy is being used or it's spent by the body to moving from surface of Earth to infinity, and this much is left. So you can, this is total energy, this much is spent, the left is.